Hello, this is Dr. Gardner. We're going to be looking at some calculations to determine the percent yield in your precipitation laboratory that you've performed. I thought a few of the calculations were somewhat challenging, so I'm going to walk you through some very similar calculations. Now, please note that the values for masses and the different amounts of starting material or products that we collect in these calculations have been changed slightly. That's because I would like you to actually put in your values collected experimentally when you do these calculations. We'll look at a few of the post-lab calculations and how to set those up as well, but realize that I have also changed some of the values, so you need to run through the calculation with the values in your handout to get full credit for the laboratory. Now, I want to look at part one, where we're first taking our calcium chloride sample and adding sodium phosphate to it. In the laboratory, we're adding an excess of my sodium phosphate, which allows me to simplify my calculation. Now, I know I'm using an excess of sodium phosphate because in the laboratory we ask you to add sodium phosphate until we no longer see any more white precipitate forming. At that point, we're assuming that all of the calcium chloride that was present in your solution has completely precipitated out as a calcium phosphate product. Okay. Now, if we begin with a relatively large sample, this is going to be a much larger sample than you actually will have used in the laboratory. So make sure when you perform your calculation for this step that you use the actual mass you weighed out. Now, if we use 5.51 grams of calcium chloride and add an excess of sodium phosphate, we can assume the calcium chloride is my limiting reagent, limiting how much product I could form. This simplifies my calculation, so I will only have a one-step calculation rather than having to predict the limiting reagent in case I hadn't known which was in excess. Now, to practice problems where you have to find the excess reagent and have to perform two calculations to determine that, go ahead and look at my stoichiometry tutorials followed by my percent yield and limiting reagent tutorials. Those will walk you through several other examples where we have some slightly more complex calculations, and they will well prepare you for our exam on limiting reagents, so make sure you use those to your benefit. Now, the very first step for this type of problem is I need to write the reaction equation. And then I need to make sure it's a balanced reaction equation. Now, I've helped you with this because in the laboratory handout, we were told that we had 3 moles of calcium chloride reacting with 2 moles of sodium phosphate to yield 1 mole of calcium phosphate and 6 moles of sodium chloride. Now, if we use 5.51 grams of calcium chloride, we can do a stoichiometry calculation to predict how much of my calcium phosphate would form, assuming this was my limiting reagent that we began with. So I take the 5.51 grams of calcium chloride, and I want to convert to moles so I can do a stoichiometry calculation using my stoichiometric ratios, also known as my molar ratios. So I'm going to convert from grams to moles first. In order to do so, I need to divide by my molar mass of calcium chloride, which is 110.98 grams of calcium chloride for every 1 mole of calcium chloride. As you recall, I determine my molar mass by using the formula for calcium chloride, finding the entire mass components from the calcium and chlorine content of calcium chloride. Now, once I've divided by my molar mass, I'll have moles of calcium chloride. At this point, we can determine the moles of calcium phosphate that can form in the reaction by using my stoichiometric ratio. I have 3 moles of calcium chloride reacting as every 1 mole of calcium phosphate forms. So I use a 3 to 1 molar ratio. 3 moles of calcium chloride to 1 mole of calcium phosphate. This would allow me to calculate the moles of calcium phosphate that could theoretically be produced. Now, if I want to determine the grams of calcium phosphate that I could theoretically yield in this reaction, we're going to also have to multiply by the molar mass of calcium phosphate. So at this point, I'd want to calculate the molar mass of calcium phosphate by using the periodic table, looking at the mass for my 3 calcium atoms present and my 2 moles of phosphate ions present, and then my molar mass will be that value in grams per mole. So you want to practice determining that. You should find that the molar mass for calcium phosphate is 310.18 grams of calcium phosphate for every 1 mole of calcium phosphate. So my theoretical yield here would be 5.13 grams of calcium phosphate. That's what I predict I could form as a maximum if all of my calcium chloride reacts and that it was my limiting reagent in this problem. Now, if I was unsure about that, we would also have to see how much calcium phosphate might form when your sodium phosphate had reacted. And there's actually an example calculation similar to that shown in your pre-lab discussion if you're curious about how you would set up that type of calculation. Now, Let's say you actually go to the laboratory and you collect a smaller mass than this. So the actual amount of calcium phosphate that you collect in the laboratory when you run the experiment, we're going to call that your actual yield. Okay, so I go to the laboratory and I collect 4.82 grams of calcium phosphate after I filter out my calcium phosphate precipitate and allow it to dry. Now the sample, if I want to determine a percent yield, I'm going to take this value in green here, that's my actual yield. I'm going to divide by the theoretical yield we calculated on the previous slide, times 100. This will be my percent yield that I predict that I have. So I take the 4.82 grams of calcium phosphate that we actually produced, divide by the 5.13 grams of calcium phosphate that we theoretically calculated is the maximum we might obtain, times 100. This gives me a 93.9% yield of calcium phosphate. This is fairly reasonable. Now, a few of you may end up with a yield that's greater than 100%. This most likely is due to having excess water, excess solvent present in your end sample. So if you look at your sample and it appears to still be like a gel, so it has some moisture content, you probably have that additional mass from having an impure product. The only way I can get higher than 100% yield is if I have an impurity in my product. If I had pure calcium phosphate, we should not have greater than the theoretical yield at a maximum. So I either have solvent or some other contamination present in my sample if I have greater than 100%. That would be something very important to discuss in your conclusions for the laboratory if that occurs to you. Explain what you think happened to give you that high yield. If you have a yield less than 100%, you should discuss different steps where you may have lost a portion of your sample. Now in part 2 of our experiment, we analyze an unknown mixture that contains calcium chloride. So we suspect that calcium chloride is mixed with some other white powder, most likely another ionic compound that does not precipitate out with phosphate. Okay, so if I weigh out 2 grams of my unknown, this is probably about twice what you actually weighed out in the laboratory, so use your values when you perform this calculation. But if I had weighed out 2 grams of my unknown sample, added sodium phosphate until I no longer obtained any more precipitate, filtered that calcium phosphate precipitate, and dried the sample, and if the dry sample weighed 1.06 grams, I should be able to back calculate to find out how much calcium chloride may have been there in the original mixture. So I'm actually going to perform a very similar calculation with respect to setting up the stoichiometry to what we had done for the limiting reagent problem, except we're working backwards. So I first write the balanced equation out again that I'm using. I'm going to write down that I collected 1.06 grams of calcium phosphate. Now I want to calculate how many moles of calcium phosphate that I collected using my molar mass. Then I'm going to use a stoichiometric ratio to compare to the calcium chloride that I believe is present in my original unknown mixture. So divide by the molar mass of calcium phosphate of 310.18 grams of calcium phosphate for every 1 mole of calcium phosphate. Then I use my stoichiometric ratio, my molar ratio, to compare calcium phosphate to the amount of calcium chloride that would have been present in the original unknown. Now I know for every 1 mole of my calcium phosphate, I'd have 3 moles of calcium chloride that must have been present initially. So I have a 1 to 3 mole ratio here. Then if I want to calculate the grams of calcium chloride present in my original sample, I go ahead and multiply by the molar mass of calcium chloride. So I multiply by 110.98 grams of calcium chloride for every 1 mole. So the calcium chloride in the unknown mixture I calculate would have been 1.14 grams of calcium chloride. This is less than the 2 gram sample size. This makes sense because we assume that if we had 100% purity of calcium chloride, we'd have a 2 gram sample initially from our calculations. Since we have less than this, we expect that, as we suspected, the unknown mixture is impure. So next I want to calculate the percentage purity of calcium chloride in the original unknown. In order to do this, I'm going to take the mass of the calcium phosphate that we experimentally collected. Actually, it's the mass of the mass of the calcium phosphate that we collected. I'm going to divide by the mass of the unknown sample. So here I'm actually going to take the mass of the calcium chloride. This should read mass of calcium chloride that we calculated from our experimental results divided by the mass of the unknown sample times 100. This will be my percent purity. So I'm actually using the 1.14 grams of calcium chloride for every 2 grams of my unknown sample times 100. I would have in this case a 56.9% purity of calcium chloride that I would have calculated was present in the unknown. I would want to report this percent purity in my post-lab results as well as in my conclusion to show the purity of my unknown. My instructor will be looking at that purity to determine how close I am to the actual true value. Now the next thing we're going to look at is some of our post-lab calculations. In order to help you out with your balancing of chemical reactions, in case you haven't covered that in lecture, I've already given you a balanced equation for the combustion of butane with oxygen to form carbon dioxide and water. Now, in our example calculation, I'm going to look at what the calculation would be if I had used 76.6 grams of butane and 192 grams of oxygen. Now, since I have quantities of two of my reactants, both the butane, which is C4H10, and the oxygen, which is O2, this is a limiting reagent problem. I need to decide which one of these two reactants will run out first, which will produce the least amount of product of carbon dioxide. That would be my limiting reagent. So I'm going to have to perform two calculations. So first of all, let's start with the 76.6 grams of butane. Okay, let's find out how much carbon dioxide would form if all the butane were to burn. So I'm going to divide by the molar mass of butane, 58.14 grams of butane for every 1 mole. Then my stoichiometric ratio will be used next to find the moles of carbon dioxide I would form. So I look at my balanced equation. I say 8 moles of carbon dioxide are forming for every 2 moles of my fuel of the butane, C4H10, is combusting. So I have that 8:2 ratio for my stoichiometric ratio, or my molar ratio. This would give me my moles of carbon dioxide, and then if I wanted to calculate my grams of carbon dioxide, I multiply by 44.01 grams of carbon dioxide for every 1 mole of carbon dioxide. I'm using my molar mass here to determine the number of grams of carbon dioxide I would form. Now the answer to this calculation is only going to be the answer to the question here if my butane is my limiting reagent. Okay, so let's make sure our units cancel out. We'll see we have grams of carbon dioxide. If the butane is my limiting reagent, I will form 232 grams of carbon dioxide theoretically. Now, I need to see, though, if the oxygen might be my limiting reagent. Now, if you first glance at grams of butane versus grams of oxygen, you only have 76.6 grams of butane and 192 grams of oxygen. Some students may assume that if I have a lower mass for one of my reactants, maybe it's the limiting reagent. We cannot always assume that's true once we have to look at the stoichiometric ratio. So let's double check in case the amount of oxygen is my limiting reagent, despite the fact that I have a larger gram mass here. Okay, so I take my 192 grams of oxygen. I'm going to divide by the molar mass of oxygen. Remember, it's diatomic oxygen. It's one of our diatomic elements. It's diatomic oxygen in the atmosphere. It's the stable form of oxygen. So we divide by 32 grams of oxygen for every 1 mole, since I have 2 oxygens in its formula. That'll give me the moles of oxygen. Now I use my stoichiometric ratios, and I recognize for every 13 moles of oxygen that are involved in the combustion reaction, I produce 8 moles of carbon dioxide. So I have an 8:13 ratio for my stoichiometric ratio, or my molar ratio. That would provide the number of moles of carbon dioxide I would produce if oxygen was my limiting reagent. Now I can multiply by my molar mass of carbon dioxide just like we did at the last step of the previous calculation, which would be 44.01 grams of carbon dioxide for every 1 mole of carbon dioxide. This predicts that I would have 162 grams of carbon dioxide. Now, both of these answers can't be correct, so we have to realize the smaller of the two, the 162 grams of carbon dioxide, is what I actually theoretically predict I will produce, because as soon as I form this first 162 grams of carbon dioxide, we will have run out of oxygen gas. So we should have excess butane that didn't have a chance to combust. That's why we never reached the 232 grams of carbon dioxide in the first calculation. So my theoretical yield is 162 grams of carbon dioxide. The next question you want to ask is, what is your limiting reagent? Your limiting reagent was the limiting reactant, the beginning material that you ran out of first. So I ran out of oxygen first, so oxygen is my limiting reagent. The next thing we want to calculate is, when I actually run an experiment like this, what would be my percent yield of the reaction? So I actually have to perform a combustion reaction and collect the carbon dioxide that is produced to see how much is formed. So I run this exact same reaction in the laboratory and I collect 132 grams of carbon dioxide. This would be my actual yield. Now to calculate my percent yield, I'll have to take that actual yield that we collected when we ran the experiment, divided by the theoretical yield we had determined from the limiting reagent, from the oxygen gas that was my limiting reagent. Multiplied by 100, that will give me my percent yield. So we collected 132 grams of carbon dioxide when we ran the experiment. We had calculated that we would have 162 grams of carbon dioxide that would form based on the limiting reagent of oxygen gas running out first. So the units here should actually read grams of carbon dioxide theoretically calculated. So that's the incorrect unit, should be carbon dioxide. Multiplied by 100, that would give me 81.2% yield of carbon dioxide for my percent yield. Now, on question number 5 of your post-lab assignment, we had a lot of information about taking a mineral sample that contains fluoroapatite present in it. And fluoroapatite has a fairly complex formula. It has 5 calcium cations, 3 phosphate ions, a fluoride ion. Okay, so you will have to find its molar mass. That'll be a nice exercise in making sure you can find correct molar masses. Now I tell you, we take a 5-gram sample of the rock, of our mineral, and we go ahead and dissolve the fluoroapatite from the rock using sulfuric acid, and we produce hydrofluoric acid as a product. So here we produce 6.70 times 10 to the negative third moles of hydrofluoric acid. Now, one way to approach this problem is imagine that the mineral sample was like your unknown sample that we analyzed in the laboratory. So it's a little bit like that unknown of calcium chloride that we were looking at, except now we're analyzing an unknown rock sample. Now, I'm told how many moles of one of my products I formed, so it should be a fairly simple task to back calculate to find out how much fluoroapatite must have been in the unknown mixture in my rock sample. Just like when we found out from the amount of calcium phosphate in the laboratory that was collected, we could back calculate in the unknown and find out how many grams was present of the calcium chloride in the original mixture. So it's a very similar calculation. We just had a lot of extra text on this question, so don't let that confuse you. So I start with the 6.70 times 10 to the negative third moles of hydrofluoric acid. And my molar ratio here is 2 moles of hydrofluoric acid for every 2 moles of fluoroapatite that we form, or that we had in the original sample. So this is a 2-to-2 ratio. Even though the stoichiometric ratio, the molar ratio, is the same number, I still write it to stay in good habits for when it isn't the same value. So I always write these down anyway. Now once I have the moles of fluoroapatite that was present in my mineral sample in an unknown mixture of the rock, we can go ahead and multiply by the molar mass of fluoroapatite. So 1 mole of my fluoroapatite is 504.31 grams of fluoroapatite. This will allow me to calculate how much fluoroapatite must have been dissolved from the original mineral sample unknown. So I should have 3.38 grams of fluoroapatite that was in my original sample. And my sample size to be also 5 grams. So we can use these masses to calculate a percent purity of fluoroapatite in the mineral. So I had 3.38 grams of fluoroapatite in my original sample, divided by my rock sample unknown, which had a 5-gram mass before we dissolved the fluoroapatite out of it using sulfuric acid. So I take the amount of mass of fluoroapatite that we found from our analysis, divide by the grams of the original unknown mixture times 100. This will give me a percent purity. So I can calculate that there's 67.6% fluoroapatite by mass in the rock sample. Now we're going to work another calculation that looks at the amount of sulfuric acid that we added. So let's say we provide an excess of sulfuric acid, but we want to know just how much extra sulfuric acid we used beyond what we needed to dissolve a sample of fluoroapatite. So let's actually say that we know that we dissolved 4.20 grams of pure fluoroapatite using a 3.60 gram sample of sulfuric acid. We'd like to predict just how much excess sulfuric acid that we used that wasn't required to dissolve the fluoroapatite sample. So in this case, I'm doing a stoichiometry calculation. I start with the 4.20 grams of fluoroapatite divided by the molar mass of fluoroapatite, 504.31 grams of fluoroapatite for every 1 mole of fluoroapatite. Then my stoichiometric ratio to compare my fluoroapatite to the amount of sulfuric acid was 2 moles of fluoroapatite for every 7 moles of sulfuric acid. Once I have my moles of sulfuric acid that I need, I can calculate the grams of sulfuric acid by multiplying by the molar mass of sulfuric acid. So 1 mole of sulfuric acid has a molar mass of 98.08 2.8 grams of sulfuric acid. So the sulfuric acid that would have reacted would equal 2.86 grams of sulfuric acid. So this is what we actually needed, the 2.86 grams of sulfuric acid based on having the original 4.20 gram sample. So I can go ahead and take the 3.60 grams of sulfuric acid that we began with, subtract the mass of sulfuric acid that actually is calculated to have reacted. The difference between those numbers will predict my excess sulfuric acid that was used in this reaction. So I take the 3.60 grams minus 2.86 grams. I predict by this calculation that 0.74 grams of sulfuric acid was left over in excess. So I hope you find these example calculations useful when you perform your calculations for the post-lab. Now be careful to use the actual values that were given in the post-lab calculations, because I did change the numbers because I want you to practice setting up the calculations.